A very good afternoon to all of you. So today I'm going to do the experiment to determine the velocity of ultrasonic waves in liquid by plotting the diffraction grating pattern for laser, and to determine the bulk modulus and compressibility of the liquid. You have to determine the bulk modulus compressibility of the liquid by finding here. Wait.
एक पेज पलटना था बस.
Relax. Here, first of all, we will find lambda mu diffraction pattern say, then after that velocity, then compressibility. So for lambda mu we need to find theta for lambda mu. Sorry for inconvenience. So where we were, yes, we will find first of all we will find theta from the diffraction pattern by tan inverse d by l. The d will be the difference between the first peaks from central peak to two peaks. D will be this and this, from the central peak to two peaks distance, like this. Here, from the central peak to this peak to this peak. This is the peak, first peak, this is first peak. It is first order. Okay, so from the first order peak, from the center peak, it will be the distance d here. We will take average of both. It's 2.5, 2.5. So average will be same 2.5. 2.5 here we will put in meters, and 1 meter is L. So theta is equal to tan inverse d by L. D is this distance from the center peak to first peak, and L is 1 meter. It is given here. We have used 1 meter, right? So it's 1 meter. From there we will find theta is equal to 0.143, and lambda mu is equal to, here we will put theta value here in sin theta, and lambda mu will be n lambda sin theta. N is order, so first order, since we have taken first order. Lambda will be the wavelength which we have used, 650 nanometer. We will put these values here, and it will get 2.6 into 10 to the power minus 24. This value of lambda mu we will put here, nu into lambda mu. Nu is our frequency which we have set. It's 5 megahertz. So we will put this value 5 megahertz here, and as you can see here, it's 5 megahertz. Okay, it's clear. Yes, so we have found the value of lambda mu. Now we will put this lambda mu value here. New lambda mu, new we have seen frequency 5 megahertz, and lambda mu we have find here. These two values will give our velocity, and beta is equal to this 1 upon compressibility.
Compressibility is 1 upon beta.
Sorry, compressibility is 1 upon beta. Beta is this. We have to multiply it by density into velocity square, right? Density into velocity square. Velocity is this, velocity square, and it will be our beta factor, and 1 over beta is our compressibility. Okay, fine. Yes, so now let's move to the main important part, how we will take readings. For taking readings, here as you can see in table, first of all let me tell you the apparatus, how we will start. You can see everything is turned off now.
Wait.
This is our liquid in which we have placed
piezoelectric crystal. As you can see, this small white colored paper is the piezoelectric crystal, this one, which is connected to two wires, and it is going to the radio frequency input. Here it is from this we are giving this RF oscillator. From this we are giving 5 megahertz frequency to this piezoelectric crystal, and due to which the ultrasonic waves are created in this liquid, and so due to that standing waves are created, so it acts like a diffraction grating. So, and here we have a power supply. This goes to this laser. Here this is our laser. This is as you can see, laser type. It is diode laser. Okay, and it goes to detector. This is our detector, and this is our measurement unit. Yes, so
fine, let's start. So directly what we will do, turn on the circuit. As you can see, I have turned on. Detector is turned on. Now I will turn on the, as you can see.
Now you see, this is the laser pattern. just directly coming from the liquid without any radio frequency. Now if we turn on this radio frequency, yes, now you see the pattern change.
As we will turn it on.
Simultaneously.
Relax, turn it on. First click. You can see here two sidewise diffraction first order spectrum we have observed since standing wave formed as soon as we have turned on the frequency, and standing waves are formed and the diffraction pattern has been formed. Okay, so what we have to take readings in this way. First of all, as you can see, where is my pen?
In this diffraction pattern, first of all we have to start from one end and go till the other end. So we have to scan this whole spectrum, and with a difference of 0.5 millimeters, 0.5 millimeter position, we have to note corresponding intensities from this detector octave measurement unit.
Okay, so as you can see here, the pinhole is right here, just to the left of at my pen. Pinhole is right here, and our diffraction pattern is towards right side. So we have to do the same. We have to, like if I'm tightening our screw, then it will move towards diffraction pattern. As you can see, pinhole is moving towards diffraction pattern, and it will, your detector will increase. As you can see, you can see as I'm tightening, and pinhole is moving towards this side, means as I'm like here is my pin, and my pinhole is moving toward this side. Then detector reading will increase, since diffraction, it will move towards the diffraction pattern, and detector reading will increase. As you can see, increasing. Now it crossed the first order spectrum. Now it will again decrease. As you can see here, it's decreasing. Now after that, it will again start detecting the our main bright
Central
fringe
maxima.
As you can see here, my pinhole is at central maxima. It is not visible since it is just to the left, like I am pointing out here. My pen is just to the pinhole, as you can see. Now I am tightening again, and you can see here, since central maxima is very bright, then as I will keep tightening, it will increase exponentially. As you can see here, it's increasing, and since it's, if you will detect, turn it there, since you can't detect in, if you will detect in microampere, it will not show readings. And one more thing, initial readings, like here, for first maxima you need to take in microampere. Earlier it was set in microampere, that's why it can't. Now let me show you, like these readings. Now these readings you may take in microamperes, since they are very fine readings. As you will increase, it will not show readings, so then you need to go to the higher scale, to milliampere scale, and then as you will move toward forward, it will again increasing. Then if you see, first maxima is reached, and first maxima.
Yes, ma'am, devices. Start.
Okay, as you can see here, my pin is at just to the peak of the first order maximum. As I further increase, it will start decreasing, and it will reach to the just next to the first peak. Now again it start increasing, since my, let me make you understand by the, here in this graph, like we will have 3 peaks in this way, as you can see here. So right now, in starting, I am showing with you a starting spectrum like this. As you can see here, as I explained earlier, my pinhole, is it visible? Bring more closer. My pinhole is just here, just to the left of the first peak. It means my pinhole in graph, it is here just to the left of. As I will tight, it will keep increasing, 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 and it will go to the peak value. So as I will tight, look, I am tightening, it will increase, 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 more, more, and up to 2.1 or 2.2, 2.1. Now again it will start decreasing. Look, now I have started increasing, increase, increase. Now here, now again it will start decreasing. Now I am again increasing. Now it will start decreasing like this. Now again it will start decreasing, 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 decreasing. Now again it moved to here, like somewhere 2.1 here. Now again it will increase and increase up to exponentially too high. Now as you can see here, it's increasing and increasing, keep increasing very high, like up to how much? I think approx this one 25. Now our this peak is 25 approx. Now again it will decrease, 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 decrease. Now as you can see here, keep decreasing. Now again it's keep decreasing here. Now again it will start increase 2.1, 2.2 something, 3, 4, 5, 7, and after that now our peak is 2.7. Now after that again it will decrease, again it will decrease, and it will go to up to 0, 0. Now I am again tightening, it will go up to 0. So whole spectrum is in this such a way. Okay, now let me tell you in micrometer how you will take readings. You will take reading in the gap of 0.5, 0.5, like here. For example, lift it up, lift it up.
It's visible.
No, I want the spectrum to be visible.
Just explain the micrometer working.
Okay, okay.
It's not necessary.
Till 5. Now my micrometer is just to the 5. As you can see here, is 5 visible? You can see here 5 is right here. My micrometer is just to the counting 5 millimeter. Now I'm opening it. Okay, so as I will open, and you can see here 5, these are counting as 5 millimeter. 1, 2, 3, 4, 5. Here it's 5 millimeter, and one more scale is towards and decrease it. It is not visible. Lift it up, it's not visible.
We just have to remember that a complete rotation, one complete rotation means 0.5 mm.
Turn off the why it's not visible. Now see here, you will observe see here, you will observe 0, 1, 2, 3, 4, and it's 5, and towards right side it's 0.5, 1.5, 3.5, 4.5, and it's again 5. Now I have made simple version here in copy, as you can see here. So this main line is this, and it's just 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeter. Now how I will take reading? I need to do 0.5 millimeter gap, right? For that it's right. Now it's exactly, make sure to match the vernier scale at 0. Now I will open this scale, open, 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 one complete rotation to 0. See here, it matches to next line on right side. It means it's on one complete rotation, it is calculating 0.5. Now again I'm rotating. Now it will, for one complete rotation, 0.5 again it will move, and it will move up to 6. As you can see here, I am rotating again, it move up to 6. As you can see here, this it is coinciding with first millimeter on the right side, sorry, on the left side. Here it's coinciding with the 6 millimeter. If I again move, then again it will move to 0.5 rotation. As you can see here, on one complete rotation it moves 0.5 and matches with right side 6.5, right? Now if I again move, it will move up to 7. One complete rotation again of vernier scale, again match with 0, and it matches with 7. That's how up for 0.5 gap you need to take readings. And as you can see here, we have taken readings 0.0, 0.5, 1.5, 2.5, 3.5, like this. We have taken readings here total we have taken so many readings, like up to 49. And we have plot the graph. There is graph, as I have explained earlier. Graph will be like this. Then when you need to take this value from the center peak, as you can see, from the center you will plot graph detector output versus distance, this distance versus this distance versus detector output. Now when you will plot graph, you need to take the distance from the first peak to the central peak here on the right side, and as well as on the left side. You will take average of these two. Since both are 2.5, you will take your d value, fringe width will be 2.0025, and you will calculate your theta, which the formula is theta is equal to tan inverse d by L. This d is 0.0025, which you have calculated just right now. L is 1 millimeter, this length total, and by this you will calculate all the things, these things which I have told you earlier. That's all, it's done.